For those of you who are here for the previous talk, we were talking about dating and matchmaking, but now we're on to a technical topic. So our next speaker is a senior machine learning scientist at Adyen, and he has a background in data science research. And today his topic is going to be on identifying drifts in irregular time series, and you can already see names of 2 different techniques on the screen. So please give a big round of applause for Vitalie Spinu.
Thank you for the check. Can you hear me? Yeah. Thank you for the presentation. Indeed, I work at Adyen as a machine learning scientist, mostly on underperformance detection and explainability tooling surrounding these underperformance issues. So today I'm going to share a few of the insights / challenges / actual solution, one of the solutions which we run in production. At Adyen, we have plenty of data. So you might know Adyen is a global payment solution. It's an end-to-end platform integrating online and in-person payments. We have a full stack, software stack in-house. We also have the full hardware stack in-house. What this means, a lot of responsibility. So we have literally millions and millions of time series, which are monitored across hundreds of teams in the company. This time series range from core business data, the actual payment flows, and goes all the way to the telemetrics of the payment terminals. Right? We have, of course, like any other company of this scale, we have the data platform, we have the core hardware, the core teams. We have the ML teams with their stack. So we have a lot of trendy, drifty series. Even the terminals can drift because they age, right? The error rate might grow over time and slowly increase. But arguably the most complex data of all is the actual business core data for 2 reasons. First of all, it's economics data, right? We know economic data is very complex. It's more stochastic. It has complex patterns. It's difficult to predict. But more importantly, our data, our situation is even more tricky because we have a partial visibility into the data, into the payment flow. So we, in a sense, squeezed between 2 black boxes. On one hand, we have the merchants, their customers, a few fraudsters here and there, and on the other hand, we have the payment networks, the issuer banks, and acquirer banks. Like, we don't have the visibility what is going on the merchant side. We don't know what kind of promotions they run. We don't know their business cycles. We don't know when they screw up stuff. The same story on the other side. We don't know what the payments networks do, what sort of experiments they run, what sort of experiments issuer banks are running. Now, when we see a problem on our segment, we'll have to answer the question: is it really a problem? Is it on our side? Is it on their side? And it's very, very tricky. Now, today I'll be talking exactly about this piece of this type of data, the core payment flow data. And our team's monitoring pipeline is just a standard pipeline like you see probably in any other company. So you start with the time series, you run a detection algorithm, you assess whether it's alert-worthy. If so, you enrich it with explainability. It can be extra dashboards, extra explanation. You try to figure out automatically the problem for the customer, for the merchant analyst, for example. Finally, you send it to the interested person, potentially the actual merchant. Now, what is drift? At least in our definition. So we understand by drift, in the time series context, the drift topic is much wider. If you saw the morning presentation from Nene ML, you know that there is this concept drift, then there is some sort of aggregation, then there is a time series, which is a kind of some sort of metric. So we start with this time series, right? So our context is the time series, and we define drift as any negative deviation from a reference behavior, essentially underperformance. So I will use drift and underperformance interchangeably today. So for our purpose, we classify also internally drift into groups, and this is kind of the standard taxonomy. So there are these incremental, slow-moving drifts, right? So like over the top figure, over the months, you see the slow bleeding trend. On the bottom figure, you see trend occurring over the weeks, still very slow comparatively. The next one is the sudden drift, right? Something breaks suddenly, and that's the most common one. So that's the commonly called change points. Now, the last one is a little bit interesting. This gives us a lot of headaches. These are like, technically they're not a separate category of drifts, but it's these things which recover very quickly. And there is like a sudden drop one day and then it recovered. Of course, when you're on that day, you don't know that it's going to recover, right? So you're still interested in this. You want to report it, you want to catch it. Now, but you don't want to catch things like this. Something which regularly occurs. The spikes, we have a lot of data like this. This is mostly subscription data. End of month, there is this bump, drop, drop, drop. So you want to avoid picking these ones. If you send to your merchant analysts these sort of alerts, they'll get very annoyed very quickly, right? So now here's the challenge. Can we capture all of these problems with one simple, uniform system? Like with one set of parameters, one set of interpretation skills, one set of business logic. And it turned out we can. So our approach is essentially a 4-step procedure. Here's the time series. As you can see, it's very seasonal. Now, first step is to remove this predictable pattern. Right? Get rid of everything you can predict, all the seasonality patterns, holidays, so on and so forth. What is left we call level. Now, this level better be integrating volume. There is a lot of information in volume. Usually time series, business time series come with some sort of counts, especially rates. In this case, this is authorization rates. Now, as we will see later, it's very important to incorporate this volume into the logic of level computation. Now, the next step, take this level, segment automatically, right? Find you see the green line over here, this is the reference period. Now, this is the dip period. Finally, not in this series, but it can be a recovery period. You want to detect recovery because you don't want to send to your analyst already recovered series, right? So this segmentation is the second step. Then, given this segmentation, you decide, is it really in drift on some sort of statistical ground, right? Because the segmentation algorithm will happily take constant series, would segment that, right? You want to ensure that the segmentation which you got is really meaningful. So what you do, you compare the reference period with dip period, and finally the recovery period also with reference period. Finally, you decide if, on business grounds, if this alert is business worthy. You can have limited capacity, or you might not care about 5% drops. It's up to you to use some meaningful business metrics to decide whether to send this alert to the analyst or not. Right? So these 4 steps are there. They slightly deviate. This procedure slightly deviates from what you normally see in the drift literature, because the segmentation part is normally not there. They can assume that you have windows coming from predefined window. More on this later. Now, a few challenges which you face when you design a system like this. The first one is complex seasonality. Like business data is seasonal, right? And this seasonality overlaps. You can have hourly if you monitor refined data, hourly, daily, weekly, monthly. Some of the seasonalities are not regular. For example, months, they stretch, right? End of month, we'll have some drop in volume, for example, here, right? It will be over superimposed on the weekly seasonality, which you see these spikes here every Monday. Now, incorporating this is not entirely trivial, because most of the packages, seasonal decomposition packages, which you can find out there off the shelf, assume the regular intervals, right? So they're not immediately dealing with the seasonality, which is irregular, which is stretchable over time. Now, the next problem is missing data / irregular time series. We don't have as such missing data, the actual measurement missing data, but we have a lot of series which are intermittent of this kind, right? So wouldn't it be nice that the algorithms which do your drift detection, your segmentation, would understand this data by default? So you don't have to do some missing data imputation, you don't have to batch your data and aggregate it on intervals, and you actually cannot do. Sometimes these intervals are very long. And again, most of the packages out there, time series packages would assume regular intervals. So there are very few time packages which deal with irregular time series out of the box. Now, this is another example. We have series like this. Very rarely, but you'll see the series which occurs every month or so. The next challenge, as I mentioned, incorporating the volume. Just look at this. Look at this time series, right? There is a sharp drop over there. But actually, what you see in this point, do you see it? Yeah. What you see here, just very few observations. What happened here, you have very few observations. The authorization rate just didn't happen. Like authorization didn't happen for those observations. So naturally, when you observe little data, you have more noisy authorization rates, right? Or you have more noisy rate series. Now, if your model looks just at the rates, you'll be generating these alerts, right, which are meaningless. Nothing is going on there. So incorporation of the volume is very important, and usually it's incorporated as a weight, right? Unfortunately, very few packages allow for weighting, at least in the Python ecosystem. So next challenge is the actual segmentation, right? So how do you figure out where is the reference? Right? We have these patterns, we have the series which have some sort of stable behavior, then they change the behavior, then there is a new normal behavior. Right? What we want to take the new normal. We want to take only the most recent segment which is relevant, right? Because in this particular case, it looks like this stuff is going on already for a few months, so this is the new stable. So I want the algorithm to automatically figure out the beginning of the reference. And our algorithm is trading off the recency and the magnitude. So higher the point, because we're interested in higher time series, and like this is the rates, higher is good. Right? So here, for example, you would see an example of stepwise behavior, stepwise drift. Right? So there is some level, then it drops again. Now the algorithm in this case picks this one as the reference. So it, in a sense, trades off the recency and the magnitude, right? And it's a global optimization, as you will see. It's a global optimization, so it kind of trades all these things together and figures out the optimal reference period. Now, this is another example. You have a series with multiple problems, right? So which dip you'll pick? You have two dips. This one is like more stable, and this one which occurred more recently, right? But generally, you see this long-term kind of droppy behavior, then some recovery. By the way, this is the recovery which was automatically detected, but it's not fully recovered all the way to original. Now, generally speaking, we don't care if there are multiple problems, right? As long as the algorithm shows us a problem, as long as you can send the actual problem to the analyst, we are good, right? So we're not very sensitive to which one to pick. But generally speaking, you see there is a trade-off between like recent drops, further away drops, and this happens automatically. And it's also configurable, so like you can actually trade off. All right, so after the challenges, let's actually get into the concrete procedure and start step by step. First one, remove regular patterns. So what we do, we have actually a pretty simple algorithm, and it's inspired by a recent algorithm called MSTL, which is in turn an adaptation of a classic algorithm called STL, a seasonal trend decomposition. So what seasonal trend decomposition does, it decomposes the series into the seasonal part and the trend part. Only one season. Now what MSTL does, it loops this STL into outer loop and estimates multiple seasonal components. So essentially, for every season, there is a running kernel, right? You see this thing over here. So what you do, you have a running moving average, which you estimate one season. You remove it from the series. You have another window. You run it again. You remove another seasonal component. And now you repeat in a loop. This is it. This is pretty much it. There are several layers of complexity. For example, you can do this weighting moving average. You can also do the weighted linear regression, for example. Right? The same story. You just move over, you isolate one seasonal component, then you isolate another seasonal component, and so on and so forth till convergence. Remarkably, this algorithm converges very fast. You just need like a few iterations. So what we did, we took this algorithm and adapted it to irregular time series, because original algorithm works on the index of the time series, right? So you have 0 to n. Now, because we have kernels, those kernels can work directly on the calendaristic date times. There is no reason why they should work on the index. They can just happily work on the actual dates. And here you go. You make this adaptation. Of course, you need to tweak a few things, but this simple adaptation make it work on the regular time series. Because suddenly, the index is no longer improved. You don't need to batch your time series. You don't need to aggregate your time series per time. You just work directly on the time series with missing data, on time series which is regular. All right, very nice. This is an example. You take a time series, you have the trend component, you have the weekly component, you have the end of month component, and you also have the smooth monthly component over here. Right? So like generally, because you have this kernel system, you can build in arbitrary seasonalities, arbitrary calendaristic seasonalities. And these seasonalities can be just like simple dummies. It could be sinusoids, which like stretchable sinusoids if you think about months. It can also be some localized dummies in a sense, like if you're estimating something for Thursday, then you look not only on the previous Thursday, but you will also look at a nearby Wednesday and Friday, for example, right? Or later. You can have sort of this smooth, fuzzy dummy. So you can incorporate this sort of pseudo-fuzzy dummies into the system. So a lot of flexibilities. And we know that, right? The kernels are very flexible tools. Now, very briefly, I put what is available off the shelves. I'm sure there are other things, but these are like the standard libraries, skTime, stats model, more recently, the Nix class, stats forecast. So you can go and you actually have the standard decomposition techniques. On the left-hand side, you see the probabilistic ones. These are generally very complex computationally. They also require an extra skill. You basically need a PhD level in statistics, I think, to really fully understand what's going on. On the other hand, the right-hand side, these are the smoothers, right? The moving average, the STS, MSTS, and this MIST algorithm, which we labeled this as like extension. This is our algorithm for irregular time series. Now, 2 points I would like to mention. We can talk about this more and over time, but the weighting part. Like weights are very important, as I showed you earlier, but unfortunately, none of the available off-the-shelf packages have this ability to incorporate the weights. But it's possible. All of these algorithms can actually do that, right? For example, in probabilistic models, you will just weight your likelihood when you do maximal likelihood optimization. Or in the smoothers, because these are just averages, you have the weighted averages, right? So it's very easy. So there is no reason why weights wouldn't be available for these algorithms. Another point, which I find very cute and simple, like look at this MIST. It's both offline and online algorithm. How could it be? And Essentially, if you have an algorithm which works in irregular times and also has the weighting, you effectively can construct an online algorithm. So look at this series. And now, you're interested, more recent data, you're interested in the patterns like, hourly, monthly, hourly, daily, so very regular intervals. But more you go in the past, these hourly patterns are no longer relevant, right? The daily patterns are no longer relevant. So what you do, you gradually start aggregating your data, right? So you aggregate here into weeks. Then after a few months, you aggregate them into months, because you don't really care what, like 3 years ago, this hourly data. Now, this allows you to compress the original hourly data, like, thousands, tens of thousands of observations, basically into a few hundreds, right? And into constant length. As a result, and this constant length, 200 observations, these smoothing algorithms will run on millisecond time. So effectively, it's a constant computational time, millisecond level, and you have your online algorithm. And this aggregation is also an online algorithm, right? It's just like you add the last observation, you shift the data, so it's very computationally efficient. I thought this is cute. The next level is segmentation, right? The next step. So what we use the DTW, and DTW is the dynamic time warping. What it does, it's a famous algorithm to match the two series. You have a pattern, right, or a query, and you match it to the reference series. Now, every point on the query will be matched to one or more points on the actual time series. So what we have this reference period, we have the deep period, we have the recovery period. In this particular case, there is no recovery period, so what happens? The recovery pattern is now matched to one point, the last point, right? So everything is just like, all these points will be matched to one point, right? Then the deep will be matched to actual deep. And this is really the characteristic of this algorithm. Even though you have the pattern like this, if you have just a sharp drop, all the deep and recovery points will be matched to that drop, right? So as a result, you have this automatic algorithm to select the reference, to detect the deep and recovery. Now, what is not widely known is that these algorithms can have this one side, left side, or both sides free. Like usually when people talk about DTW, people think about, okay, matching one complete time series to another complete time series. But what you can actually do, you can leave one tail free. So what we have, okay, we pinpoint to today the most recent observation, but the another tail is free. And of course, the pattern itself is a parameter, is a hyperparameter which you can tune for your own purposes. Now, the next step is pretty simple. Once you have the segmentation, well, simple, relatively simple, you can use any statistical test to actually take the difference, right? You want to compare, okay, is this difference significant, right? And you can use a lot of options here, right? Like standard tests, you can do bootstrapping tests, you do permutation tests, and you can do whatever is available in standard drift libraries. Now here comes the difference between what we do and the standard libraries. Standard libraries start from the window. So they ask you to specify the window, the training data, let's say window, and then the new data. So the reference and the new data are pre-specified, so the segmentation you still have to do yourself. And this sometimes, a lot of times it makes sense because in machine learning context, you have the training data on which you train your algorithm, and then you have the new data, online data, test data, right? So it's pretty straightforward. In our case, we have the time series segmentation. We don't have these intervals. Yeah, the last step is the actual business decision, right? So once you have the segmentation, once you have the business metrics, you make a decision, right? And again, you can do some sort of cumulative metrics, like days ongoing, total counts, cumulative unexpected loss. So you think, okay, there is the reference, what happens if it continues? Now it drops, what's the difference? This is kind of unexpected drop. It can be both average, it can be cumulative. Of course, if it's cumulative, that you might have the situation that there is a small drop, but then it accumulates over months. And if you're, expected value optimizer, then you care about these small drops which go forever as much as you care about the drops which happen suddenly and have bigger magnitude, right? Of course, if you're talking about predicting the future, let's say what will be my loss tomorrow or next week, of course you care then about the average magnitude, right? So it's all a trade-off. And I think this is it. Thank you very much. So your questions. Yeah.
Thank you very much for a brilliant talk. I have experience of solving the same problem for payment system, and my challenge was to decrease the detection time. And from my perspective, dynamic time wrapping cannot deal with fast detection of these segments. Maybe you deal with it, with such kind of problem with different instruments. And you need to detect the fast in minutes, in hours, not in days or in past.
So even though the data which I was showing is daily, in our experience, like while applying this instrument, even 1 day is enough. If the magnitude is, if you have the sharp drop, which you're talking about, the DTW will just happily squeeze everything in that point. I didn't show you pictures, but this is what is happening. Like, we happily detect these single drops. I don't know what will be the explanation, but it's all about this global optimization. If this single drop is big enough, right, then you will spend a lot of loss, right? It's a global optimization of the loss, so you'll gain a lot of loss by squeezing everything in one point. So it does actually work pretty well in our experiment.
Oh, thank you.
Questions?
And by the way, you have a control, you have control, you can nudge your algorithm for the time refinement. For example, if you're interested like in a weekly drop, then your pattern can be of weekly length. If you're interested more in a monthly drops, monthly patterns, then your pattern will be monthly. But nevertheless, it will still catch the quickly varying patterns just as happily, right? You just nudge it a little bit.
Minutes drops.
I mean,
Minutes drops.
yeah, that can be, right? It depends on your, I mean, the refinement, the step of the time series doesn't really matter. Yeah.
Yeah, thank you. Could you maybe shed some light on how those weights corresponding to the volume, how they link to the significance test for your dip? Because I can imagine that if the test is significant, that also says something about the volume, right?
Precisely. So 2 points. One is that all these 4 steps, you can integrate weighting, right? All of these 4 steps are plug and play. So you can put whatever you want there. But each of these steps ideally should be understanding weighting. And for the actual test, the non-parametric tests, like for example, permutation test, Mann-Whitney U, there is no weighted equivalent. Actually, because you don't have distributional, well, it's not a distributional form. We don't know the actual distribution of this level, right? Then normally non-parametric tests will be better, but they're generally non-weighted. It's kind of difficult to integrate weights into the, for example, Mann-Whitney U test, but there is some like recent discussion, there is a blog post where the fellow tries to actually figure out this problem. But then you can use like bootstrapping tests, for example, which can be weighted. Right? So each of these steps can handle weights, and of course, if there is very little data or more data, you better be taking that into account during the test phase, right?
Hello.
Hey.
Thanks for the presentation. I have a question about the reference and the drop. If you have any metrics, how can we evaluate whether we are fair with choosing the reference and the drops?
Oh yeah, that's a hard question. That's very hard. Like, you need labeled data, right? So it's extremely time consuming. We started this initiative, but because of the priorities, it's not yet completed. But you basically have to label the data according to your business case, You look, okay, this looks like a good decomposition, this looks like a good decomposition. Sometimes, on some series, you have multiple decompositions, and human eye perceives them as like both okay, right? So it could be multiple truths, in a sense. But in order to validate this algorithm, you really need the label data.
If you're too shy to ask questions, well, we have one more question.
Hi, maybe to add on to the last question, if you have labeled data, have you tried LSTM for doing this kind of anomaly detection?
Oh, no, not yet. Didn't get that far. But it's not entirely dissimilar, right? Because the DTW, what it does, it's a dynamic programming algorithm, right? So it kind of detects these three segments automatically by optimizing it globally, right? An alternative would be to segment it somehow, right? And then combine this, like, for example, change point detector will give you like a bunch of segments, then you'll combine them. But it seems like more troublesome, right? And recursive models, like LSTMs, right? I wouldn't know immediately how to use it. Like, seems to be quite complex initiative would be. I wouldn't know how to use it. Well, never tried. That's my answer. Yeah.
Hello, thanks very much for the presentation. You mentioned you dealing with millions of time series. Do you cluster them in any way or try to find similarities to try and
Indeed.
simplify
There is an ongoing project on our side to do this smart grouping in a sense, what you refer, because there is quite a bit of redundancy, especially hierarchical type of redundancy. And we will be able to eliminate quite a few of these, hundreds of thousands and millions of time series which we operate. The good news is that even though there is quite a lot of redundancy, it's not bothering us that much. Like, we rarely see, but it's, 2 or 3 time series which kind of indicate the same problem, but that's okay. So far, it wasn't a problem. This is why this project wasn't prioritized. But yeah, we're looking in that direction to reduce in a smart way, to aggregate, and still be able to monitor on this very refined level of observability. Yeah, there is a question.
Thanks. For the first step for getting the level, or for how much expert knowledge do you use, and how much sort of weird seasonality, like public holidays in different countries, do you apply for these? Is that the standard?
So indeed, this is a good point. This is, in a sense, what we call inductive bias, right? We don't, the model doesn't learn the pattern themselves. We kind of put it on top. But we know our time series. We know that it's weekly. We know that it's monthly. We know that there is this weird pattern, which is actually coming from subscription data. And generally, recurring subscription don't happen after the date of 28. So what you'll see some spots here every month, except of February, when you'll have these holes basically in the data. This is very, very common. So we have this expert knowledge, right? But that's pretty much all of it, right? You plug the standard specification, like 5 different seasonalities, which we see across of them. If in that particular time series, this is not that pattern will be just 0, right? You're not estimating anything, so it doesn't really harm. But if it's there, you pick it up, right? So expert knowledge is really minimum. You kind of know, like, it's a trivial information in a sense.
One last question.
Yeah, I have one more. Do you consider the multivariant variation? Because, for example, if you consider an authorization for one merchant, it could be easily splitted in different payment methods. And you can, for example, have a gap in Visa, but everything okay in MasterCard. And here you should consider multivariate, highly correlated time series in it.
So this series, this is why we have millions of them, because they're already split on these groups, right? And now it connects to the smart grouping idea. Okay, how do we actually reduce this redundancy? For example, if the problem is systemic for a merchant and it occurs for MasterCard and Visa, then we report it for that merchant and they say, okay, it occurs everywhere. But if it occurs on MasterCard, you just get to the MasterCard. So at this moment, we are monitoring them at this highest refinement level, which we decided upon, some business logic. But eventually, we would like to do something smart, to do this multiple correlation, automatic grouping, and reduce the redundancy in a sense, right? Because the main problem is that you have the same problem but occurring in multiple places. You don't want to report 10 series, right? Maybe next PyData. Yeah.
We have reached the end of our time for this talk, so if you have more questions, you can still reach out to Vitalie. Meanwhile, we have something for you from PyData.
Yeah. Thank you. Thanks. Nice stuff.